Oh, okay. Okay, got it.
All right, any progress for the four students who have come in late? We have been doing the integer programming problem this time. So please find the share the lab notes and go to the integer programming section. You should work in groups of 2. And we have 5 minutes left. Any questions? I provided some hints for this problem. So one is that you might want to use, when you do in Excel, choose BIN to stand for, that stands for binary in terms of constraint. And when you construct the constraint formula, you should consider using zeros for no and ones for yes. Then afterwards, we are going to solve it together and see whether you have most of the steps correct or not. Okay.
Do you remember it was
Oh, that's
With all the 3 components to formulate the problem in words, expressions, and solve it in Excel.
I don't like it. Oh, no. I last time. Okay, we'll go back to the. It's basically, yeah.
Oh.
Okay, so that's the total. Okay, now we just. Do you want to write it? Yeah. In the middle. No construct 2 sites. There was no constraint on the site. The reason why these are fixed is because within our costs cover all sites.
Okay, here, let's see.
Right here, either. So I changed the yes and no to binary. Leave the and then apply.
Answer here
Like
was
here.
incorrect.
Left hand side.
Yeah, I think that should be 11.
So
I think it should be.
well, you got 2 extra minutes.
Oh.
Ah.
We have not written it in words yet, but I just want to see like what's our answer. Like, there should be 1.
We got 3 and 4, yes.
Yeah.
Let me see. Yeah.
Yes.
Correct.
Okay.
But your sheet of paper.
Yeah, we're
that
still,
you
we're still
can-
writing it out.
Oh, okay, all right. Now you have a competitor.
No, why do you say integer? You have biz. He says biz. Yes.
Yeah, so BIN stands for binary, in case you wonder. And there's another option that's titled ITN, which stands for integer.
I need to change this out.
Yeah, you just do 1, 2, 3, 4, 5.
Any groups about to get to the answer? Oh, you ready? Okay, let's see.
I know, but really hard to set these as big. It says, yeah, it says, it says, it's not- it's set them. It doesn't matter. When you type it in, like, we'll check it. Wait, I still got.
Has an updated answer. That's
Oh.
Let me sure.
Yeah. I don't know why it's not working. Okay. Essentially.
Perfect. It did they ask for your ID?
Yeah.
Then what did you say?
You don't have it, don't ask for ID.
Really? Well, I was able to get my own without showing my ID. So. Do you want to try at a different time?
Hey, where to keep going back?
No, it's really like that.
Wow, okay, it looks brilliant. I mean, did you also, oh, okay, also looks good. So, and by the way, it's supposed to require your ID and your meal plan, but you just say, I forgot to bring my ID. I think it should work. I'm not sure why, these two couldn't get it done, but do you want to kind of, or maybe Starbucks, or maybe one of each?
Oh, yeah. Yes, I was. Yes.
Oh, that one?
Yeah, then you can come back. All right. Now we have a winner here.
Take Starbucks.
Okay.
Did he grader?
Oh.
Because they came earlier. They're the first.
Ooh, I will also take Starbucks.
Okay.
Thank you, thank you.
Yeah, that's why you just say, I forgot to bring that. It's fine. All right, but let me take a look. It's probably also a correct answer. Yeah, and yeah, looks good. Although We are also supposed to, describe the formulation, not just the example. Yeah, so let's start working on that together. Question? Oh, yeah, you want to get this thing back because. All right. Now we start to work on this problem together, and what you can do is, well, let's see whether it actually makes sense. I was thinking that each of the team exchange your worksheet between teams so you can grade or sort of see how the other work does. You don't need, you won't be graded by the correctness, but just so that you understand which step you did correctly and which step can be improved or it was incorrect. So let's start working on that together. So to solve this problem, we need to first understand or extract information from it. I conveniently included this table for your convenience, but such a formulation of the table may not be available, for example, in exam questions. So we should also understand. We should also understand what we need to do to get some of the information here, which will facilitate how we construct the problem. So usually, well, of course, the first part, that's the accessibility matrix, needs to be provided. That's the source information. However, these two rows about capacity and cost can be extracted directly from the question. So these two rows may not be provided directly. So we should be able to get here from the question words, phrases. So for example, when we mention capacity, it says that the total demand is estimated to be 1,000, whereas the capacity or supply, the maximum supply from each site will be 500 until 600. So that's how I got this row. Because here in the table, we really have the decision variables on columns and all the constraints or some other information, or usually they're coefficients on the rows. So we have one row about the capacity coefficients. And there's one more row about cost. These are also about these are coefficients when we construct the objective function. So now we have all the parameters needed for this question. So let's start working on that. So for this binary integer program, as demonstrated in earlier mathematical programming problems. First step is that we want to extract parameters, which we already did in this table. This may not really needed as any answers in exam because these are actually provided through the question, right? But what we need to do is to understand it so that we can translate them. Next step is that we want to define decision variables. So in this question, the decision variables are, well, I will just define them as xj, where j belongs to 1, 2, 3, and 4 to representing whether or not a charging station, well, a station should be built at site I. So here we should say that xj equals to 0 if not to build, and xj equals to 1 if selected to build. So here, what's different than the discernibles as we practiced earlier in our grocery list and the water supply problem only lies here that all the discernibles needs to be binary. By binary, we mean that we use 0 and 1s to represent a whether or not. So it's a there can be only 2 cases. So that's step 2, where we define decision variables. And it appears that I have both words and mathematical expressions done in the same step. In step 3, we do the objective function, right? So we, in words, I would say that the objective is, well, to minimize the total cost. So this is an implicit objective, although none of this question phrases mention that, oh, we must minimize the cost. But since in our problem, we have the cost associated with building at one of each site. So automatically, we should think about how we can minimize the total cost. And in mathematical expression, it'll be that the decision variable, the objective function, is to minimize a variable symbolized by z. It equals to, let's see, now here these coefficients are going to be helpful. We use time x1 and 150 times x2 plus 190 times x3 plus 250 times x4 to represent the total cost. Well, so you could also see z represents total cost. So here we effectively claim the objective function as a function of the decision variables. Here all the xj's appear, right? So that's what links the objective function represented by z and all the decision variables we just defined. So last time, some of you had a difficulty in finding the correct answer in Excel solver. Many of the times, it occurred because we did not successfully define the decision variables or constraints as a function. So it must be a function. When we think about a function, we do, for example, in this case, it's a linear combination. We need to make a calculation between the decision variables and the coefficients. So any questions here, how I arrived at this objective function? Oh, brilliant. We should understand here that this step is nothing different than we practiced last time. Since the decision variable is again a linear combination, well, the objective is again a linear combination of the decision variables. Now it comes to constraints. So the constraints come in, let's see, 2, 1, 2, 3, actually 3 components. So in words, I would say that the constraints are, let's see, part 1, the accessibility, right? So that's what pops up in the first rows in the table. So when we talk about accessibility, okay. all these constraints are also sort of binary because we have yes and no's, and in the hints I provided, we usually use zeros for no and one for yes. What it means is that, let's see, first, for residents from region A, they are able to reach a station if it's built at site 2 or site 4. If the stations are built instead at site 1 or 3, according to this table, residents in A won't be able to reach the stations in at site 1 or 3 within 15 minutes. So it won't help them, it's too far away. Instead, for residents from, for example, region D, they can benefit if the site is selected at 1 or 4, but they won't be able to reach sites at 2 or 3 if they were to get there within 15 minutes. So let's see how we can use this information to construct our constraints. So I would, for example, do this in region A. It'll be 0 times x1 plus 1 times x2 plus 1 times x3. And again, oh, well, this should be 0. And 1 times x4. We constructed the left-hand side of the constraint, saying that if a charging station is built at site 1, it doesn't really affect residents from region A because the coefficient is 0. However, if it's built at site 2, if it's built, then x2 equals to 1, right? And in front of it, the coefficient is 1. So the usable sites or usable charging stations for region A will equal to 1 if x2 equals 1. Similarly, no matter whether there's a charging station at x3, so whether x3 equals to 1 or 0, it doesn't really affect the number of charging stations available to residents in region A. Similarly, if a site is selected at 4, so there's a station at site 4, region A residents can reach another station. So possibly they can reach, either 0 or 1 or 2 stations, right? No more than that. Then how do we do the right-hand side? So since this is supply, right, this should be greater than a demand. So now let's think, if you were one of the electric vehicle owners, do you really care that whether I can charge the car at 1 or 2 stations? Maybe you don't. So as long as there are at least 1 that you can use, you should be okay with that. If there's more than 1, well, of course you can choose between those 2, but it'll be as if you were provided with 1 station, right? So that means the right-hand side should be greater, should be 1, and the relationship, the operator should be greater than or equal to. So as long as there is at least 1 station available to residents at site 1, it's good. So do you understand the logic here? Any question? How I arrived this piece of constraint? All right. Then with that, we continue with site B. So we do that by following the coefficients in the table. If it's yes, plug in 1. If it's no, plug in 0. So for residents from region B, they are able to do it if it's built at site 1 or 3. So all these are 0, right? So I would just make it more simpler. You should do the linear combinations yourself. This is also greater than or equal to 1. For C, we also have a, okay, so this is yes, 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 and this is no. For site D, we have a yes from site 1 and 4. These are 0. So please complete all these constraints. So they are linear combinations between the coefficients, either 0 or 1, and the decision variables from x1 to x4. Each of them has equal to or larger than 1 on the right-hand side. So that's the accessibility constraint. So here we should, in words, say that there is, well, it's just omit that part that doesn't carry essential meaning. We should say that at least one station is, within, well, within 15 minutes for region A through D. So that's exactly what we did here. We guaranteed, we want to guarantee that each of the region has at least one station that's available within 15 minutes. Because the accessibility matrix here represented by yes and no already carries the 15 minutes constraint inside. So using the 0 and 1s of coefficients will include such constraint. So we don't have to write 15 anywhere as one of the coefficients. All right. In addition to accessibility, we also have the demand and supply, right? So automatically we should claim that the supply is no less than the demand. Okay, how do we achieve that? I added another row updated in our shared lab notes about the capacity, right? This is effectively just like what we did in the water supply problem. If site A can contribute up to 500 cars serviced per day, we time 500 and x1. So if x1 equals to 1, then it represents we do have a station at site A. So it adds another 500 of capacity in the total capacity. If x1 instead equals 0, we don't have a station at site A, so we cannot enjoy this extra 500 units of supply per day. We do the same for the other sides. So this is 300 times x2 plus 450 times x3, and last piece is 600 x4. What about the right-hand side? Now you should be very familiar, right? Any tentative answers? Is this a greater than, equal to, or smaller than or equal to? Any answers? Yeah. So because left-hand side, what we just calculated here is called the left-hand side value. It represents supply, right? As we said earlier, the supply needs to be no less than, so it means greater than or equal to. So great answer from there. And right-hand side should be the demand. And in the question, we see that the estimated demand is 1,000. So we just completed the supply and the demand constraint here. Any question in this step? All right. Last piece is that we want to claim everything in the decision variable is binary. Although we defined it already as binary, but we also need to supply this constraint as a constraint to Excel. Otherwise, it doesn't really understand what xj's needs to be, right? So here we need to claim the binary constraint. So we can say that all decision variables are binary. It means x1 is equal to either 0 or 1. So here, effectively, I can say this. So xj belongs to 0 and 1 as a set. So it equals to either 0 or 1. All right. Now we have all the constraints. Then the fifth step is to, let's see. We can, yeah, we can altogether formulate it as minimize z. We can transcribe this part here and subject to this represents subject to all the constraints. So we have a first constraint. We forget down here. Second, second piece of constraint goes here. Third piece of constraint goes here. So that's the mathematical expression altogether. Now, in the last part, let's see how we can solve all this in Excel. So on the shared screenshot, you can see that's how I formulated this problem in Excel using the exact information from here. As we can see, just like what we did last time, we have one row in blue representing the 4 decision variables. Well, in the beginning, you should probably have empty cells before the Excel provides you the solutions, right? And I use all the green cells to represent coefficients or constants. So all these values in the green cells are constants. They are not functions. They won't change no matter what we do to the rest of the Excel sheets or cells. For example, for the objective function, I have this 203 through 250 as the coefficients. As you can see exactly here, I have all the constraints. I mean the coefficients of cost. Then using that, I can calculate the total cost. As shown here, it's represented by a sum product function. Sum product function, as we demonstrated earlier, is nothing but a sum of products. What sum are products? So the products here is from between C3 and C6, and we sum that to a product between D3 and D6, and so on. This is exactly what sum product is. However, when constructing the function, we always begin with a equal to sign. So you must include this equal sign to claim a cell to be a function cell. Otherwise, it will stay as a constant. It won't change no matter what you do to the other cells. When doing so, for some product, you should select one row or one column as the one side of the multiplier and another row or column as the other side of the multiplier. So here I selected one row of the x's, so the xj as one row, and all the coefficients of the objective function as another row. So that's how I can calculate the objective function. We do the same for the left-hand side values of the constraints. These left-hand side values, as shown in yellow, they are all function cells. You can confirm whether you defined the cell as a function or not by going to Formulas tab, and there is a button called Show Formulas in the Formula Auditing section. When you click it, all the cells defined as formulas will show the function name. If you don't see this function name, it means your cell was not defined as a function. Instead, it may be a constant. So it's incorrect. It won't change. So once we confirm all these yellow cells actually are function cells, so their values change with along with our decision variables, we can continue. So each of the left-hand side values are again a linear combination between the decision variables and the constraint coefficients. Once it's defined and we successfully recognize each of the constraint has equal to or larger than operator, right-hand side values are 1000 for capacity and ones for demand, and ones for the accessibility. We can go to data and use solver. So this time we have solver. We have the decision, the objective function in this yellow cell representing total cost. we have we need to minimize it, and by changing values in the blue cells representing the decision variables 0 and 1s. And we have all the constraints because all of them share the same operator. So I define them as just one block. All the left-hand side values need to be greater than or equal to the right-hand side values. Then what's the extra step is that I had one extra constraint. That's the binary one. I did that by add one constraint. I select all the decision variables and use the drop-down menu to select binary, then click add, then cancel. Since all of them are binary, so they are already non-negative, so we don't have to check this non-negative button, but let's solve it. All right, let's keep the solver solutions in the sheet. So here, as you can see from Excel, it claims that to reach the optimal minimized total cost, we need to build stations at site 3 and 4, but not at site 1 or 2. So the solution is that x1 equals to 0, x2 equals to 0, x3 equals 1, and x4 equals 1. So we have one set of solution of all the 4 decision variables, and the total cost at the optimal solution is $450,000. All right, our lab session is completed. Before you leave, please turn in your sheet of paper. And I hope to see you again next week. Let me know if you have any questions. I can stay here for a few minutes.
That's fine, right? It's brilliant.